Hello friends, happy holidays to you, happy new year to you. At the request of some subscribers, I'm making this video about calculating the equivalent resistance. More precisely, I will talk about finding an equivalent resistance in the case of a mixed connection of resistors. Unlike a series or parallel connection of conductors, there is no universal formula that could be used to calculate a mixed connection. I will show the calculation method using the example of our mixed connection task. Well, let's get started. To do this, you will need to remember what a serial and parallel connection of resistor is. So, in the case of a series connection of resistor, the equivalent resistance is found by adding the resistance of individual resistor. I think this is simple, it's understandable, because the total length of the conductor increases and at the same time the equivalent resistance increases. In the case of a parallel connection, a different formula is valid, and in this case the equivalent resistance will be less than the resistance of any resistors. You need to be able to add fraction. I hope you can do it. Do not forget that at the end you need to flip the fraction. To understand how to act with a mixed connection, you need an example. I have prepared for you such an example of a mixed connection of conductors. I decided not to write numeric values. Let's deal with this without numbers. We will analyze numeric values and example later, but to understand the essence we need to learn to understand the sequence of action. So I draw some diagram and it looks like this. Let's try to break it down on the plot as I do. As you can see, resistors R1 and R2 are connected in parallel. The total resistance I have designated as R12. There is nothing to do with R3, so just I designated R3 and I designated the last part as R456. The first thing we have to do is find the resistance R12. I hope you understand that these resistors are connected in parallel, and to find an equivalent resistance you need to use the formula that I'm writing down now. To add fraction you need to make a common denominator. The numerator needs to be multiplied by the corresponding multipliers, and most importantly, do not forget to flip the fraction at the end. I don't do anything with R3, but immediately switch to the R456 section. As you can see, R4 and R5 are connected in series, and I just add up the resistance of R4 and R5, and I write the results already for the case with parallel resistance. I hope you understand the mathematics of this process, because physics cannot live without mathematics. Finally, the third action, in which we simply need to add up the resistance of the corresponding section of the electrical circuit. So in this example they are connected in series. So we got such a cumbersome answer which does not need to be further simplified. Of course, if you suffer from insomnia, you can bring the fraction to a common denominator and so on. Let's see how it works in Numeric. For simplicity, I will denote the resistor's resistance with the corresponding number. So in the first section, if you apply the parallel resistance formula, you will get the equivalent resistance of the first section of 5 ohms. I hope it's simple. As you can see, nothing needs to be done with the second section. This is 5 ohms. The third section is a little more complicated than the others, since it consists of two sections. First, we add up the resistance for a series connection of resistors, and then we apply the formula of parallel connection of resistors. And after all, we have to add up the resistances of the individual sections and get the answer of 15 ohms. Well, that's probably all for today. I invite you to follow my Telegram channel as well and follow my notes, which you can also purchase in the store by sending a message which I will leave in the comments to this video. I also invite you to buy clothes with my notes. I hope you see it in the sale of souvenirs. You support me with this. That's all for today. Write in the comments what video you would like to see. Bye bye everyone. Sincerely, Yuri Kovalenok.